But if you take a fairly naive view to trying to combine quantum mechanics and general relativity, and you actually take the gravitational field from general relativity, the geometry, the space-time, and you just naively try to quantize it, so treat it, try to make a quantum theory as you would for any other field, take the metric as the field that you're quantizing, then what you find immediately is that the actual topology of your space-time starts to fluctuate at small scales. And so you no longer have a well-defined topology on small scales. So you've actually destroyed the thing that you tried to quantize in the first place. And the kind of scale at which this happens is the Planck length, being essentially coming in, if you try to do this naive quantization, as some fundamental limit of measurability for all fields. So this actually, you could use this as an argument to say that there is an intrinsic uncertainty in the space-time metric itself when you get down to the Planck scale. But all of those arguments are mainly based on what you would now, or probably even then, call fairly naive attempts to put the two together. So in that sense, the current attempts to combine quantum theory and general relativity actually seem to accentuate the difficulties that we have in some ways. So yeah, so here's just like I say, you could give a whole book or several books on these different approaches over the years that people have attempted to actually reconcile the quantum theory and general relativity, and particularly address these problems with the local topology of space-time on small scales when you put the two together. So people have looked at lattice theories, where instead of taking a continuous space-time structure, you take a discrete space-time structure, sometimes called quantized space-time, although I think that's a dangerous word because it gets mixed up with quantizing it, and in reality, really what people are doing there are lattice theories. People have looked at alternative algebraic fields underlying everything. They've looked at non-Archimedean geometry, space-time foams, whatever they might be. First poster I made as an undergraduate had a picture of space-time foam on it. It was really good. All my friends were biologists, and they had all these lovely posters with colourful pictures. So I made a poster with lots of equations on it. I had one little picture at the end of space-time foam, which I was really proud of. You don't get many pictures in this. I had a picture of space-time foam, which was totally meaningless. I liked it. I needed to have a picture because I felt inferior. So it was just like a box with little circles in. And so associated with space-time foam, different topologies, so actually looking at what I call quantum topology. People have, this is something which has received a lot of attention over the last few years, looking at non-local loop states with internally defined the kind of loop gravity approaches. There was excitement about non-commutative geometry, quantum groups. The problem with all these things was that I think pretty much all of them, if not all of them, were very focused on this idea of trying to get rid of these problems at the very small scale, at the Planck scale. They're saying we don't have a problem with the idea of, that I put at the start, that a good way of describing the natural world is by having a space-time structure and then individually existing entities interacting on it with each other and maybe with it. All we have a problem with is the specific formulation that goes wrong at the Planck scale and gives us this fluctuating topology and things like that. So all of these are really focused on solving that very small-scale problem with space-time when you try to quantize the differentiable manifold. And I would argue that that's not really where the fundamental problem is. That's a technical problem which we typically don't have to deal with because we're not dealing with phenomena that are occurring at the Planck scale, and we can safely say that we don't actually observe quantized topology on the scale that we're familiar with. So in some ways, that's not really the fundamental problem with quantum mechanics and with relativity. The fundamental problem, to me, comes more from non-separability and non-locality in quantum mechanics, which is at macroscopic scales. This is not non-separability and non-locality in quantum theory are nothing to do with the Planck scale. They are macroscopic phenomena. And so it already calls into question the whole basic ideas that were underlying those two theories that they're trying to put together. That you have this space-time structure that's out there with its well-defined notions of locality on it, and then you try to stick entities on top of it interacting, which do so in a strange, non-local, non-separable way. And that's what you should be trying to address.
I think you should perhaps just mention that this non-locality is 41 kilometres at least.
So they've got it up to 41 kilometres.
At least.
So yeah, people may have seen theoretical treatments of the EPR experiments.
Which is pretty good for them.
Very local in astronomical scale.
Yeah, it's local in astronomical scales, true.
Right, but nonetheless it's macroscopic compared to the Planck. Compared to the Planck length, it's several orders of magnitude bigger.
And these non-local objects are the source of the continuous background as well.
Yeah. So there's a real problem here that so you may have seen theoretical treatments of EPR, as Basil's saying, the idea of entangled states moving apart, or parts of those states moving apart, shall we say. And then you can see the non-local correlations in there, but experimentally saying that's up to 41 kilometers now. Okay. So the EPR effect really does occur. It's not a theoretician's dream. And so it's something that we really do have to address if we're worried about space-time. And one approach to this is what Wheeler called pre-geometry. And there's been some recent criticism of this. There's a paper in Studies in History and Philosophy of Modern Physics from a group in Finland arguing that every approach that's called itself pre-geometry is geometric and so fails in its aim of actually being pre-geometry. So I don't want to use the term pre-geometry, although I like it. So I'm going to talk about pre-space.
Who are these guys, by the way? Remember a name?
I've got a paper here, but I can't remember their names. I think it's back at the hotel.
They're finished.
I wasn't really bowled over by their arguments, but I'm aware of the fact, just in case anybody's sat there thinking, yeah, the pre-geometry is rubbish, that you could argue that you still have geometric notions even in pre-geometric theories. So that's Wheeler's term for it. I don't want to use that term because it does have problems. But what I mean is that we've heard about process and implicate order already from Basil, that the approach I'm putting forward is that we have, as our basic description of the natural world, process rather than these individually existing entities. And that the process is happening without any space-time. And that space-time comes from the process as well as the entities that we see in the explicit order as interacting on that space-time background. And this is what I mean by pre-geometry. And whether that's geometric or not, I don't care. What I really mean is pre-space-time. Because you could, basically what they're arguing is if you've got any ordering in your process, then they're calling it geometry, because you've got ordering. So it seems a fairly empty argument, but just in case anybody's worried. So what I would have called quantum pre-geometry, I should call quantum pre-space or quantum pre-space-time, is the idea that what we're using as a representation of the process is coming from our understanding of quantum theory. Because in principle we could say the description of the underlying process is something completely different to anything we know in physics. Because we have a problem with the implicate order approach, where this idea that what we see in the manifest world, the explicit order, is constantly unfolding and enfolding into an implicate order. What we know as the laws of physics are just telling us how one explicit order